Welcome to this deep dive into econometrics and data science. Today, we are demystifying one of the most common yet frequently misunderstood phrases in statistics. A one-unit increase in X is associated with a beta increase in Y. While it sounds simple, the nuance behind these words is what separates a basic analyst from a true expert. Let's peel back the layers of linear coefficients. To understand coefficients, we must start with the foundation, the simple linear regression model. Represented as y equals beta 0 plus beta 1x plus epsilon, this equation is a mathematical abstraction of reality. Here, beta 1 represents the slope. Geometrically, it's the rise over run. If we move one step to the right on the x-axis, beta 1 tells us exactly how many units we move up or down on the y-axis. But remember, in the real world, units aren't just numbers. They represent years of education, dollars in salary, or milligrams of dosage. One of the most critical aspects of interpretation is the scale of measurement. If X is measured in dollars, a one-unit increase is just $1, often an insignificant change. However, if we rescale X to represent thousands of dollars, that same coefficient beta 1 will effectively be multiplied by 1,000 in its interpretation. Misunderstanding units is the leading cause of magnitude errors in policy reporting. Always check your descriptive statistics. What is the standard deviation? Is a one-unit move even realistic for this variable? Now, let's move into multiple regression. Here, the interpretation becomes ceteris paribus, a Latin phrase meaning all other things being equal. When we interpret beta 1 in a model with multiple predictors, we are looking at the partial effect. We are mathematically holding constant all other variables, like age, experience, or location. This is visually akin to looking at a single slice of a multidimensional cloud of data. It allows us to isolate the unique contribution of one specific factor. But what if the relationship isn't a straight line? This is where logarithmic transformations come in. In a log-level model, a one-unit increase in X is associated with a beta 1 times 100% change in Y. This is crucial for variables like income or population, which often grow exponentially. Conversely, in a log-log model, we talk about elasticity. A 1% increase in X leads to a beta 1% increase in Y. Choosing the right functional form changes the very language you use to describe your findings. Finally, we must address the causality trap. Just because we say an increase in X leads to doesn't mean X caused Y. In observational data, a coefficient often represents a difference between two groups rather than a change within an individual. Unless you have a randomized controlled trial or a robust quasi-experimental design, you should use cautious language. Individuals with one additional unit of X tend to have beta more units of Y. In conclusion, interpreting coefficients is an art of context. It requires knowing your units, understanding your functional form, and being honest about the limitations of your data. By mastering the one-unit increase, you turn raw numbers into actionable insights. References: Woodridge J.M., 2019, Introductory Econometrics, A Modern Approach. Gujarati D.N. and Porter D.C., 2009, Basic Econometrics. Angrist J.D. and Piskey J.S., 2009, Mostly Harmless Econometrics.